Good afternoon, everyone. How are you guys doing? Doing all right? Okay, so get started. Okay, so now we have a microphone working. All right, guys. So we have to do many things today. We need to catch up with the last part of elasticity and recurrence. And then hopefully I'd like to run a few experiments today to talk about tensile strength. So let's get started with this general solution for a mechanics problem. What we have seen so far, for example, computing horizontal stress or computing rock compressibility, those are very simple one-dimensional cases of application of mechanics to some of our problems of interest. But in general, we can also solve what are the stresses and strains in a reservoir as a function of the space in a very similar way to what you do with reservoir engineering. Okay? So in general, let's imagine that you're interested in a problem of hydraulic fracturing, and in that problem of hydraulic fracturing, you have a horizontal wellbore that goes into the phase zone, and from that horizontal wellbore, you have a big fracture here, and let's say that there is a smaller over there, that somehow in this region, before you arrive over there, there was a fracture or a fault that causes your next hydraulic fracture to deviate and go like this, so it's not planar anymore. And here you have another one that probably grows into that direction. And in this complex problem, your objective is to get to know, for example, what is the state of the stress in a position right over here. So what is going to be the vertical stress, what is going to be the horizontal stress? If we have shear, what is that shear going to be? And in order to solve that problem, it's going to be a lot more complicated to what we have done so far. But it's not impossible. And I like that we discuss about how we can do this and how actually this gets solved, for example, in a hydraulic fracture simulator. We'll just talk about the theory, but you will see it's not too different to what you are doing in other areas. So let's start, before we write the questions for this kind of problem, let's start with something that you know very well, which is a fluid flow problem. Do you remember what are your fundamental equations in reservoir simulation? Something that you really need to fulfill in order to write those equations and run the simulation. Darcy, okay, let me write Darcy over here. And what else? Conservation, mass balance. Okay, it's the same. And let's call it mass conservation. So, mass conservation, if you were to write in mathematical terms, it will tell you that you need to conserve the mass in a system, right? And that means also that the summation of fluxes has to be zero in all directions. But in order to get flux, we use Darcy equation. And Darcy equation in 3 dimensions, we can write it as Q1, Q2, and Q3, which is equal to permeability divided by viscosity times the gradient of pressure in direction 1, gradient of pressure in direction 2, and gradient of pressure in direction 3. These are partials, it's a derivative. So with Darcy, then you get what your flux is, and it goes from high pressure to low pressure zones. And mass conservation tells you that the variation of these fluxes in space, or the summation of these variation of these fluxes in space, has to be equal to 0. So Darcy law, very simple, right? You have piece of rock, Q is proportional to K and the difference in pressure. Mass conservation tells you that if you have a porous solid, everything that gets in has to get out, either in this direction or in that direction. To make it simple, let's say that there is flow just in one direction. Everything that gets through this phase has to go out through that one, unless it gets conserved in the middle. Well, you put these two equations together, and then you get what is called the Laplace equation, where look, there's Q1 over here, but we know what is Q1. Q1 is this one times that one. So I can combine those two, and I will get to an equation that looks like this. And this one is called the Laplace equation. It's just a partial equation, partial derivatives equation, and this one equal to 0. And this is basically what you do in reservoir simulation. It's a little bit more complex when you have two phases, when you have changes in composition, when you have relative permeabilities. You know how to do that better than I do. And just put everything together, and that's what you do. It's a partial differential equation. That's how you solve fluxes in space. Well, with mechanics, it's very similar. Instead of your Darcy equation, you will have what is called a constitutive equation. In our case, we're going to use elasticity and linear elasticity. And instead of mass conservation, we're going to have momentum conservation, which is basically equilibrium equations. So if it's in equilibrium, then there is a momentum conservation. And we put those two together, and we get to an equation that looks, it's a little bit long and scary, okay? But don't worry, guys, I'm here with you, so you don't get scared, okay? It looks like this. But it is exactly the same principle to the one that we discussed in flow. Just put the equations together, and you get to a big equation that if you solve, you will be able to obtain stresses and strain as a function of space. And as in this problem over here. So instead of now getting our field of pressure, that's what usually get as a solution in a reservoir simulation equation, now what you get is a solution for this vector u, where u, which is unknown, is a displacement vector. If you remember, we obtained strains from displacements. Strains were a function of displacement, so as soon as you obtain displacements, then also you get strain. And since we know the relationship between stress and strain, which is given by this equation, also we get to know stresses. And these inverted triangles over here, these are just derivatives. For example, this one, and apply to that operator, it's just something that looks like this. It's a vector dx1, dx2, and derivative in direction 3. And this one over here, for example, that double looks like a squared inverted triangle, but it's actually double. This is similar to that one. It's a Laplacian operator. But these are just derivatives, okay? I don't want you to remember exactly what these are. I just want you to remember that here we just have derivatives. And this is just a partial differential equation. And once you get to solve that, you solve any problem of mechanics. One more thing over here that I didn't say what that is. These two guys are just elasticity parameters, which are called the Lamé parameters, in which mu is just equal to the shear modulus, and lambda is equal to, it's a function of the Poisson ratio and the Young modulus, and looks like this. But it's everything that you know, elastic parameters, displacement, then you get strain, and derivatives. Yes?
In the Laplace operator, should dx3 also be squared because you didn't square it in either equation?
Yes, I always forget those.
Thanks.
You solve this differential equation, and now you will be able to tell me what are the stress and strains in this location. This is the equation that is used for a hydraulic fracture simulator to tell you how far the fracture is going to go, what is going to be the width, if it's going to go through some of these layers or not. It's just solving this equation of elasticity that for which we know all the fundamentals already. So we're not going to get into that, but remember it's as easy as that. Just solve a mechanical problem, and then you can tell what are going to be the stress and strains in any place according to any boundary conditions. Something I forgot here, similar as in fluid problems, we have boundary, pressure, or flow conditions. In mechanics problems, you have boundary conditions of displacement. Like for example, in this case, this mass of rock is not moving downwards. You have stress boundary conditions. For example, here we have an overburden, and you may have also stresses from the sides. All of those go into this kind of mechanical problem. What we're going to see is some analytical solutions of this complex equation to some more or less easy problems. So let's review those here. So the solutions that we're going to see for a general mechanics problem, some of them are going to be analytical. For example, when we get to talk about wellbore stability, we'll talk about Hirsch solution, which is the solution for stresses around a wellbore. Later on, when we talk about hydraulic fracturing, we'll see the approximations from Griffith, and this one is valid for a fracture in elliptical with elliptical geometry. But in general, usually you solve these equations numerically. And when you use them, solve them numerically, for example, what you use in the reservoir simulator, and you get to code in Reservoir 2 is finite differences, and simulators like the one that you use in Reservoir, like CMG, they also manage geomechanics, so you can solve these equations with finite difference also with for geomechanics with CMG, but most solvers use the finite element method. It's just a method to solve all these equations. And this is what, again, what a hydraulic fracturing simulator uses. We're going to get to talk a little bit about these hydraulic fracturing simulators later on when we get to hydraulic fracturing. But as I was telling you, it's just solving that equation. This is the acceleration term, which in most cases is just gravity.
So we have this displacement equation, and then we have the diffusivity equation by combining those Darcy's law and continuity.
Yes, this equation. So you put these two together, and then you get this one. You put this one together with this one, and with the rule of strains as a function of displacements, and you get that one. If you're interested in seeing the full solution of this, or how to get to this equation, I can send you a video. Okay? All right. So that's how you will solve a general problem of mechanics. There's one more thing that I'd like to discuss with you before we go to breaking some rocks. I need to talk about real rocks. We have made many assumptions that do not correspond to real rocks. And when you want to solve real problems, you're going to have to deal with real rocks. So let's try to see a few of them. The first thing that we have assumed, which is not real in the nature, is that rocks are isotropic. And what that means that